Okay, I've just gotten the information that the recording has started, so I would say we get started with the session. So welcome everyone to this virtual ICSE session on verification and validation. We have 6 papers in this session, and we will run them in the same format that most of the sessions are going, I believe. We will do 5-minute presentations in the beginning, just going through all the papers. That sometimes is a bit awkward, but that gives us an entire block of 30 minutes to discuss the papers. If you have questions, you can write them in the chat at any time and we'll get back to them. And ideally, you write to whom the question is, to which paper or to which speaker, so that we can make it easier associating. Then you can also raise your hand. I actually haven't seen how that shows up on the screen, but I believe we'll figure that out. So if you want to ask in person, that's of course also nice. So those are the rules for here, and I will be chairing this session. I'm Grisha Liebel. I'm an assistant professor in Reykjavik in Iceland, so very far up north, and it's a bit too early right now. But that's all for me. This session is not so much about me. So let's start with the first paper. And the first speaker is Ralf Hoch, and the paper is verification of consistency between process models, object life cycles, and context-dependent semantic specifications. Please go ahead, Ralf.
Okay, thank you. So, hi everybody. My name is Ralf Hoch. I'm a researcher with the Technical University of Vienna in Austria. And today I'm going to talk about our journal first contribution, where we deal with different kinds of models and how we can connect them together and verify if these models are consistent with each other or not. Just to give a short overview of the problem statement and set the scope of the work a little bit, we are specifically interested in cyber physical systems, and specifically the ones where we have some sort of process engine that drives the overall system. So for example, if we consider a charging operation for an electronic car, then first we have to insert our credit card, we get authorized, then we can connect the charging cable, then the voltage can be applied so that the car is actually charging, and then the charging process starts. So here we have a very process-oriented, task-oriented view on the overall system. So we have always some sort of action that alters the state in which the system is. And that's typically one view that's very common with cyber physical systems. On the other hand, however, we typically have artifacts that we operate on. And these artifacts commonly are designed by a different process designer, by a different person. And in these artifacts, we actually model what kind of attributes and what kind of object lifecycle these artifacts have. So for example, in our e-charging example, we could have our car as an artifact, and this artifact can be in several states. For example, the charging cable can be connected, it can be ready to take voltage, it can be charging, and so different kinds of attributes can be set, and they might have to be set in some sort of order so that we don't violate any restrictions that we have on these artifacts. And one of the questions that we are interested in is how can we bring these different kinds of models together? So how can we bring the process-centric and the artifact-centric, so the complementary view on this overall system together, and how can we formally connect them? And after we have established this formal connection, how can we use it to check and verify if these two models actually fit together formally? And here we are interested in basically in two questions. First of all, can the process always continue with a next action? So can we always reach some sort of defined state? Essentially, don't we get stuck along the way? And the other part is, can the artifact or the object lifecycle that we have in a given state always handle the action that the process is trying to execute? So for example, we cannot start charging when the cable is not connected, for example. And these are the two questions that we defined for consistency between these models. And our proposed solution is that we want to use semantic specifications to bring these models together. And these semantic specifications essentially model what one action of such a process does. So it models what has to be fulfilled before we execute this action and what needs to be, or what's ensured after we have executed it. So essentially pre and post conditions. And these pre and post conditions, we formally ground them using first order logic in our extended object lifecycles, in the artifacts. So we establish a connection between our pre and post conditions by grounding them in these artifacts, and then we're using these semantic specifications and annotate the tasks in our process model. And this finally brings these two models together, and then we can perform a consistency verification between the process model, the artifact lifecycle, and our semantic specifications. And then we check if all these models and all these parts actually fit together. We have defined an overall workflow for this verification approach. So first we start with simple models that can be given in, for example, let's say for the process-centric part of the system, it can be PPMN or UML activity diagram, something similar. And then we use model transformation to incrementally extend these models. So first of all, we add the annotations through our semantic specifications. Then we transfer the model again. We combine it with the object lifecycle, and that bring everything together into a single model. And then we use this model to transfer it to finite state machines so that we have a valid input for our verification tool that we use, which is essentially model checking using NewXMV. And we generate source code for NewXMV through model to text transformations. Together with this source code and our consistency criteria, which we see down here, which relate to the two criteria that I mentioned before, which are here given in linear temporal logic, both together, we plug it into the model checking tool, into NewXMV, and then the model checking tool tries all the combinations and checks if there are some violations regarding these two consistency criteria. If we have any problems, then we get a counterexample and we have to fix and find out how this problem did arise. If there is no problem, then we have a guarantee that we are consistent between the model regarding these two criteria. We have already used this approach in several research projects and now also with industry partners with some larger scale cyber-physical systems, and have received good results. There are still some limitations to our approach, specifically when it comes to concurrency within projects and parallel execution of different kind of paths in one process. And that's also what we are currently working on. So that already brings me to the end. It's a very short overview. If you have any questions, please refer to the paper or to the presentation online. And if you have any questions, you can always just shoot me an email and I'll try to get back to you as soon as possible. Thank you.
All right. Thank you, Ralph. Then we directly go on to the next, and that's Geetam, presenting verification of ORM-based controllers by summary inference.
It's visible, right?
Sorry?
Is my screen visible?
Yes, it's visible. It's just not in presentation mode yet. But
All right. Now it's fine,
yeah,
right?
perfect. All right.
Okay. Hi, I'm Geetam, and I'll be talking about verification of ORM-based controllers by summary inference. Our goal is to infer functional specifications from ORM-based controllers. ORM is essentially a programming technique that the application developers use to interact with the underlying database in an imperative fashion. Our functional specifications capture one, values for the model attributes. That's the data presented to the end user. And second, the database updates. Let's take an example. Let's take a look at an example controller. So in this controller, we are iterating over this user payments table. And in case this condition ID equals the incoming parameter default payment ID matches, we set the default field of user payment to true. In the other case, we set it to false. And in both the cases, we save the iterator back to the database table. In this case, our approach will infer the specification that the updated value of this user payments table is union of these two relational expressions. In the first one, the ID matches this default payment ID, and in the other case, it doesn't. In the first case, we project the true value for the default column, and in the other case, we'll project the false value. An application of these summaries is verification of a single controller. So consider this example property, which says that no tuple in this updated value of user payments table whose ID did not match the incoming parameter should have its default field set to true. In practice, we verify these properties by offloading the verification conditions to Alloy. Our approach to capture these summaries broadly proceeds in two steps. First is conversion of code to a relational algebra based IR, and second is conversion of loops to relational expressions. Let's take the same example. This step is sort of a rewrite step in which we rewrite each of the statements such that their RHS is a relational expression. So for example, in this statement, user payment list gets all the tuples in user payment repo. Therefore, we will rewrite it to say that user payment list equals user payment repo. In case of loops, we'll preserve the header and we'll rewrite its body to equivalent conditional expression. Next, we convert the loops to relational expression, and in this case, we'll rewrite the loop such that it says that the updated value of user payment repo is its initial value minus user payment list, and then union of the relational expressions that we just saw. How we actually do this translation is through a pattern-based rewrite system. These are essentially rewrite tools, and as with other rewrite tools, they have a pattern LHS and a pattern RHS. Both of them are essentially relational expressions, except they can also have these meta variables in angle brackets. How these meta variables get their values is when we match the pattern LHS with the result of step 1. Okay, we proceed with the matching and we fill up these table that gives the values for the meta variables. Okay, and then we plug in the values of the meta variables in the pattern RHS, and which gives us the summary for user payment repo that we earlier saw. You can also use this summary to check property of traces. So consider this workflow that in an application you created a user and then you went through a bunch of let's say unrelated controllers, and then you tried to look up that user that you created by say its last name. Now, interesting property that you would want the application to hold would say that if you created a user and then you try to find that user, then it should show up in the results. How we actually do this trace property checking is through these two formulas. This is the base case and this is the inductive case, but I will not go into the details of these formulas or why this is correct. For the same, please check out the paper. We implemented our approach based on dbridge, which is a work by Imani et al. At Sigmund 2016. They replaced loops with equal and sequel. That's more performant. On top of it, we add several features necessary to check functional properties. We did our experimental evaluation through the help of a bunch of student volunteers, and it consisted of these 6 open source web applications. Our results were fairly encouraging, and a large chunk of the property fell into the true categories. We also did our mutation study, and which demonstrated that our tool is fairly able to catch bugs in case they are present. We compared our approach with Java Pathfinder as baseline, and while JPF also correctly classified 16 assertions at passing, it required significant manual effort to convert Spring controllers to pure Java. To conclude, we propose an approach to capture functional specifications of ORM controllers, a pattern-based loop rewrite system, then an approach to check trace properties, an implementation, and finally an extensive evaluation consisting of single controller properties, trace properties, baseline comparison, and a mutation study. Thank you.
Thank you, Geetam. And because I haven't mentioned it yet, so the first paper was a journal first paper, but all the other 5 papers are on the technical track. So Ralph had the extra challenge of presenting a long journal paper in 5 minutes. Great. So let's continue with paper number 3, and that's Ron RefD, refinement types for valid deep learning models. Please go ahead and share your
My
screen.
paper title is
Okay.
Yeah.
Sorry.
it's my turn or
Yeah, it's your turn, exactly.
my paper title is not okay.
Then just
Yeah, can you see
tell
my,
us what your paper title is when you're ready.
my title is data-driven
Yeah, sorry.
learning. Okay.
Yes, I get. Sorry, I dropped one line. My confusion. So yeah, it's Rongchen, and it's a different title. Sorry. Please go ahead.
Okay. Hello everyone. I'm Rongchen Xu from Tsinghua University. I'm glad to show our recent work on program termination analysis. The termination is a crucial liveness property for a program. A lot of work has been devoted to the analysis of program termination for a long time. However, termination analysis is still challenging. The data-driven method has been applied to many fields in recent years and has shown its unique advantages. In recent work, we attempt to integrate data-driven approaches with the termination analysis. Look at the right program with a single loop. In the loop, the variable x keeps increasing when it is less than 10. Otherwise, it will be returned to 0. Obviously, the program is always terminating. But how can we strictly prove it? For all input x, we can find that the loop must iterate no more than m equals minus x plus 11 or 1 times before finishing. We call such the m a loop bound for the loop. This is a main framework of our approaches. Initially, the default loop bound m equals 0 and the dataset h is empty. In the analysis, we will generate a verification task for current loop bound m and check whether it is valid. If current loop bound m is valid, we can report the program terminates. Otherwise, we can produce a config example during the constraint solving and update the data set. Then we can learn a new bound and repeat the procedure. There are two crucial problems here. One is how to learn a loop bound, and the other is how to check the loop bound. We will further discuss them in the following slides. We use a random test to generate the data for the bound learning. During the test, we collect two kinds of information. One is X. The program stays at the loop head. The other is IDC, which represents the remaining number of iterations before the execution terminates. Thus, the loop bound learning problem is to find a loop bound candidate M such that for all data in dataset MX is greater than or equals IDC. In our paper, we proposed 3 kinds of loop bounds, including simple loop bounds, conjunctive loop bounds, and lexicographic loop bounds. In this presentation, I will introduce the first 2 bounds briefly. Suppose the current dataset for the right program is the triangle nodes. We can apply a simple loop bound learning here. Simple loop bound learning is an optimization problem. The optimization target has 2 terms. V-cost makes the bound result closer to the data points, and the M-cost makes the form of the result more simple. However, one simple bound may not fit the whole dataset tightly. Thus, we proposed the conjunctive loop bound learning to learn more local features. Our conjunctive bound learning will use a clustering algorithm to convert the problem into several simple bound learning problems. Bound learning, let's consider how to validate the bound. Given a program and its bound candidate, we first transform the bound validation task into a safety property problem. For example, we inserted the red code in the original program. Then we made a bounded model check-based quick bound check. That is, unrolling the loop k times and checking whether the bound is correct. The quick bound check can help us falsify an incorrect loop bound in a short time. Finally, we use a safety checker to generate an invariant and exhaustively prove the loop bound. Note that our invariant synthesizer is also data-driven, so we can share the data between bound and invariant learning and make the termination analysis more efficient. Based on our approaches, we implemented a prototype tool called DDL10. We compare our DDL10 with 4 state-of-the-art termination analysis tools. Our DDL10 solves 136 benchmarks, and the average solving time was 5.43 seconds. In the favor of cumulative time for solving benchmarks, our DDL10 extends further in solving time and grows slowly in cumulative time. That's all of my presentation. Thank you for your listening.
Thanks, Rongchen, and I'm sorry for the mix-up with the title. But now we continue. So now we get to the REFTI paper, and that's Yanji presenting that one. Let's try that again.
Okay. Okay. I will introduce our recent work, REFTI. Hello everyone, I'm Yanjie. I will introduce REFTI, refinement taps for valid deep learning models. Deep learning models provide many configuration options for users to tune. For example, the hyperparameters. User can tune this CNN model, convolutional model. For example, it contains many subgraph configurations. This one, user can tune the kernel size. Each node represents the kernel size of the conv2D. The red one represents the user tune the hyperparameter and train a new model to get better learning performance. User can also tune the neural architectures, for example, the subgraphs structure. We called it neural architecture search. But during this process, user may meet many type errors of deep learning model. Type errors is similar to the traditional programs definition. For example, the program's constants, variables, and methods error behavior. Recent impure studies indicate that type errors of DR models are not uncommon. For the first related work, it shows the incompatible tensor shapes. The second is from the industry impure studies, also show the tensor mismatch in the largest class of DR-specific job failures root cause. Let's see an example. This is a deep learning model defined by the PyTorch framework. This will trigger an illegal shape error. The root cause is that the kernel size of operator average put2D is too large, so that the height and width of the output tensor will be negative and trigger an runtime error. Type errors of DR model is very important. It can save significant shared resources on platform, boost the development productivity, reduce failures for deep learning training jobs, benefit AutoML tools to improve search efficiency. But it is very challenging. First reason is that the hybrid programming paradigm adopted by DR frameworks has the internal computation, not like the traditional program language for C++. There exists a large number of possible hyperparameter combinations and neural architectures. We summarize the common type errors of deep learning models. It contains two large dimensions, for example, the hyperparameter error and the tensor error. Hyperparameter error contains the illegal value, improper value category. Error contains 4 categories: unsupported format, illegal shape, incompatible shape, and incompatible element type. So we propose REFTI, refinement types for valid DR model. REFTI refine each operator with logical formulae that describes computational requirements on both tensors and hyperparameters. Checking the validity of a model is reduced to a constraint satisfaction problem. REFTI utilizes SMT solver to obtain the unsatisfiable hyperparameter values before job execution. We also show an example of the refinement type of MATMO, the matrix multiplication operator. Other operators will listed on the paper. the P1, P2, and P represent the constraints for the input and tensors constraints. For example, the element type constraint, the shape constraints. We also build the Rafty as a tool. Rafty will accept the computation graph, model specification, and tool specification as input. It will traverse the computation graph following the operator execution dependency to generate a set of constraints that the DR model should satisfy. We also evaluate Rafty effectiveness on individual DR operators and real-world deep learning models. We also evaluate the efficiency in constraint solving comparison with relative work Pythia. We use a precision recall and speed up to measure Rafty. First, let's show an example for the evaluation on the real-world DR models. We tune the hyperparameters and the operators. Rafty achieves 100% precision recall in all the experiments, confirming its effectiveness. We also compare Rafty with the static shape checking tool Pythia. Pythia is a shape checking tool detects incompatible shape errors for TensorFlow Python programs. Rafty still achieves 100% precision and recall, although precision of Pythia is 100%, 12.2%. Next, I will summarize our work. We have presented Rafty, a frame type-based approach for statically checking common type errors of deep learning models caused by tensors and hyperparameters that violate the computational constraints. We demonstrate that Rafty is very effective to detect potential type errors before job execution. Thank you.
Thank you, Yanji. So that was paper number 4, I believe. Yes, and next up we have Harrison Green on fuzzing, graph fuzz, library API fuzzing with lifetime-aware data flow graphs. All right.
All right, hi everyone. I'm Harrison, and this is GraphFuzz, library API fuzzing with lifetime-aware data flow graphs. This is work I did for All Secure along with Thanasis, and I'm really excited to be able to share it. So the problem we're trying to solve is how to automatically test APIs. And in this work, we focus specifically on C++ APIs, like this example here, but a lot of the ideas generalize to other types of APIs. So a well-established automated testing is fuzzing. And the idea with fuzzing is you basically create a wrapper function, like this fuzzme function here, that takes in a big chunk of data and does something with it. For example, maybe it calls a parse image function. And the idea is the fuzzer will invoke this function millions of times with different data to explore the space of your target. But a lot of APIs, for example, the C++ library, don't have a nice, convenient entry point that accepts a big chunk of data. And instead, what we're interested in is testing the interaction between many small functions. So how can we do that? Well, the main idea with GraphFuzz is to represent API interactions as data flow graphs. So in this graph, vertices represent API endpoints, in this case functions, and edges represent objects that are passed between endpoints. So created by some endpoints and consumed by others. In this case, we have a method on the canvas object. So as inputs, we need a canvas object and a point object. And after we invoke this function, we can reuse the canvas endpoints. They would also be outputs. So you can imagine converting your whole API surface into a set of endpoints with expected inputs and outputs. For example, here we have a canvas constructor that produces a canvas object. And similarly, we have a canvas destructor that consumes a canvas object. And so with this representation, the problem of generating a new test case becomes, how can we link together a bunch of these endpoints so that all of the edges are connected and the types match properly? So an example of a complete data flow graph representing a single API interaction is shown here. On the right, we have our graph representation with vertices and edges, and on the left, we have equivalent C++ source code. Notice how on the right, all of the edges are fully connected and the types match properly. Additionally, with this representation, we automatically enforce proper object creation and deletion. So we can be sure that we're calling our canvas constructor before invoking canvas drawPoint. And similarly, after we invoke that, we can be sure that we're properly calling the destructor. This representation also allows us to perform high-level structure-aware mutations on the test case sequence. For example, here we've added 3 new functions and we've properly linked it into the graph. On the left, you can see what the equivalent change would look like in source code view. Importantly, GraphFuzz can perform this mutation and execute the resulting API test case without recompiling anything. And this allows us to efficiently mutate the API sequence and test it during fuzzing. During our research, we applied GraphFuzz to a bunch of open source libraries, and we found bugs in nearly all of them. So here are 4 examples of crashing test cases that we found with GraphFuzz. Skia is the graphics library used in Chrome and Android. RDKit is a cheminformatics library written in C++. And SQLite 3 is a database library written in C. It's worth noting that all 3 of these libraries have been fuzzed very extensively, and yet GraphFuzz was able to target new API surface and find new bugs. So using GraphFuzz is fairly straightforward. The first step is basically to create a schema, which is written in YAML, and it contains basically a list of all of the objects and methods that you want to test. For the majority of the time, you can actually just list the function signature and GraphFuzz will automatically infer the expected inputs and outputs. In some cases, it's necessary to be a bit more explicit about that. And so we also have a more verbose endpoint definition format. You can look at our pre-recorded presentation or our documentation for more details about that. And then using this schema, you use the gfuzz command line tool to automatically generate harness files and then compile them with Clang using the fsanitize fuzzer flag. This produces an executable that you can run to start fuzzing. As a bonus, because GraphFuzz uses libfuzzer under the hood, the generated executable is a native libfuzzer binary, so it will automatically work with any fuzzing as a service infrastructure like OSSFuzz. And finally, GraphFuzz is completely open source under an MIT license. We've included a bunch of Docker images with all of the fuzzers we built during our research, and we've set up a website with all the documentation and a bunch of introductory tutorials to hopefully make it easy to use. Contributions are welcome, so if you have questions or ideas for improvements, please feel free to open an issue or submit a PR. Thank you.
Excellent. Thank you very much, Harrison. Now we're 5 out of 6 talks through. It's also good to see that the room is a bit fuller and we have the first questions in the chat. If you have any questions, please post them there. But for now, we have paper number 6, and that's Yilu, and the paper is Morist, model-based RESTful API testing with execution feedback. So at least we're staying on the API level now. Please go ahead.
Okay. Hello, everyone. I'm Yilu from Nanyang Technological University, and I'm going to present our work about RESTful API testing. This work has collaborated with our industry partner, Huawei. So cloud computing plays an important role in current cloud platforms. Therefore, the robustness of cloud computing services is critical. Bugs may lead to cyber attacks, which cause financial losses. First of all, let me introduce what is a RESTful API. A RESTful API means a constraint of REST style. So currently, RESTful APIs are widely used in cloud services. So one of challenges in RESTful APIs testing is how to infer API calling sequences from open API specifications. For example, how can we get these calling sequences from its specification? We proposed a solution named RPG based on the property graph. We encode response schemas and operations into it to solve the calling sequence generation. So this figure shows the detailed workflow of Morist. First, to test the RESTful service, Morist first takes its open API specifications as input to build the RPG. And after building the initial RPG, Morist uses to generate calling sequences and replace the API calls in the call sequences with actual requests. Then the generated test cases are fed to the target RESTful service, and Morist shall collect the responses. By analyzing the collected responses, Morist reports the detected failures for bug analysis. Moreover, Morris also used the responses to refine the RPG by adding missing edges and removing invisible edges. The refined RPG is then used for generating more test sequences. With the open API specification, Morris can build the initial RPG consisting of nodes and edges together with their property or labels, which may contain false edges or missing some edges. So here we introduce how Morris to use RPG to generate test cases. In general, this requires two steps. First, Morris to traverse the RPG and aggregate visited operations from calling sequences. And second, Morris generate concrete input for the APIs in the sequences to build test cases. We generate parameters on the fly by these three ways. So the initial RPG generated with open API specification may contain errors. While doing the testing, new edges are added to our RPG when we find new dependencies. As for the edge deletion, this operation is recognized as invisible after several tries. We aim to answer the following research questions with the evaluation. First, the code coverage of Morris. Second, the bug detection of Morris. And finally, the RPG guidance and dynamic RPG updating with the performance of Morris. So benchmarks contain 6 services from previous work. We use 3 state-of-art black box RESTful service testing techniques as baselines to study the performance of Morris, which include RESTler, RESTSgene, and EvoMaster. So according to the data, Morris achieve better code coverage and robustness in most cases. Besides, Morris achieves the best performance in bug detection. So RPG and dynamic updating enhance the bug detection and coverage of test case generation. So finally, we proposed Morris, a model-based black box RESTful API testing technique. And Morris learns from the open API specifications to build a RESTful property graph. Finally, Morris can use RPG to guide high-level guidance for code sequence generation and refine the RPG with execution feedback. So that's all of my presentation. Thanks for your listening. If you have any question, I'm very glad to answer it.
Thank you very much, Ji. So that, just to make sure I'm not getting it wrong, no, that brings us to the end of the presentations. Thanks a lot to all the speakers. And we jump right into the Q&A. And there was a question from Gitam to Ralph, or several questions. So maybe we start there. What language are the process models specified in? So those cyber physical system processes, how are they specified?
Yeah. Typically, they use different kind of models and languages that we use. For the overall specification of the system, we typically use SysML. So that's the overall system where we describe it. So there we describe requirements, components, how they are all related to each other and connected with each other. Specifically, the process models that we used, we did use UML activity diagrams, but we did also use BPMN diagrams for more business-oriented software. So there it's more a software, it's not a cyber physical system, but their BPMN is commonly used, and we actually support both of these approaches with both these languages with our approach.
Mm-hmm. At this level, I was wondering, because I don't think you mentioned it in the talk now, to what level is your approach specific to certain notations? Like what notations do you support, or is it agnostic?
No, specific notations that we use are the UML activity diagrams and BPMN, so the business process model notation. These are the two specific models that we use, or notations that we use. There is, of course, an option to use a more abstract process description language, process calculus, something similar like that. But for actual models that we create, it's always UML activity diagrams or BPMN.
Okay, and the other part of my question was that basically, like, what is the use case of your work? Now, I'm kind of assuming from what you said that it's actually kind of for debugging like design issues. So before you actually go ahead and implement the system, you kind of like
exactly. Yeah. I was just getting to that part. There are different kind of use cases. Typically, we try to use it beforehand, before we start with the implementation. So it's the overall design of the system, and we want to make sure that everything fits together. And then the implementation of the actual services. So all these tasks that we have in our process model are then represented by implementations given as services that we can call. And these services also have to adhere to the specifications that we have, so essentially the pre and post conditions, and there can be some relationships and abstraction within these semantic specifications that we have. So we can apply them in different kind of contexts. We can enhance them depending on where they are used, and we ensure this by using a subtyping relationship between the task in the process model and the actual service implementations that we have. So typically, as a use case, we do it beforehand, before we start implementing, but very often it's the case that there already exists some sort of implementation, and we need to enhance it with models, because everything is only implicitly given in the source code and no explicit model are available. And what companies that we are working with are commonly trying to do is to extract all this knowledge and have some sort of representation in a model form. And then we start backwards. So we have the source code, models are created, and then we see if everything fits together. So that's actually the more common use case that we have, but we actually designed it to be the other way around.
Okay, great. So, I mean, can you also like kind of disclose like which kind of clients are you working with in the industry?
You mean in which kind of domains we are working in?
Yeah, and I mean, yeah, maybe if you could also say the companies. I mean, yeah.
Okay, yeah. Yeah, I mean, I can mention the companies. That's not a problem. We have a couple of industry partners in the automotive industry. For example, we are working together with Bosch, and we're working together with Siemens, for example. So that's two larger companies that we're working with. Other companies are more local in the Vienna region. So smaller companies, but these are the two big ones.
Okay, great.
Okay, thank you, Ralph. And maybe then we directly continue from Ralph's question to Rongchen. Maybe you just discuss it directly, but I don't have to read it. I think that's
of course
nicer.
Yeah, of course. In your talk, you mentioned that you randomly generate test cases and inputs for your loops to then generate the data that you use to identify the bounds. So I was wondering how you make sure that these test cases, or that you can find some sort of class, so how many kind of test cases do you generate, and couldn't there be some sort of static code analysis useful to do beforehand, so that you have an idea where your test cases or some of your inputs are, so that you have a better idea how you get the bounds?
Yeah, the test case, we use a random test. First, the program is relatively simple in our benchmarks, so the test is relatively cover all the possible execution traces in the program, and thus we can make we can get the most information of the program from the test information with an guess bound, and to check the bound and yeah, this is the main procedure.
Okay, so essentially you're looking at the code, all kind of different paths that you could take. It's more like a white box testing that you're looking at the source code and then you're trying to find all the paths, then you generate the inputs for them. If I get that correct. Okay, thank you.
All right, thank you. And then Harrison had a question to Yenji.
Yeah, he answered in the chat, but I can discuss it as well, I guess.
Harrison's topic, the question is a very important topic. So once Raft is about has supported operators, and we also do operator reduction, because for the activation operator, they will share the same rules. So for new operators, user need to refer the source code or fuzz testing to add new rules to the tool. So it will pay some efforts to that. But this also has a very can be auto extract or generate the rules. So we recently have a cooperation with other colleagues. So we try to use data-driven or the PR technique to extract. But this is ongoing. We think that is very difficult to achieve 100% precision. Maybe it can extract some simple rules to help us. So currently, this is this problem's status.
Okay. Yeah, I mean, I think we generally see this a lot. And yesterday also in the other session I was chairing, the first verification and validation, that a lot of the approaches still require you to manually formulate first order logic, specifications, or all these kind of logics that in practice are often quite tricky for the engineers to do, right? So
yes,
that's a major issue, how to at least partially automate that.
Yes, you spend many manual effort, and some colleagues says, "Oh, I can't accept that," but we say, "Oh, this is the truth." Okay.
Okay, I have a question to Harrison. So it's an interesting idea to kind of put these different API calls together. And I was wondering, the example you made was this one of the classic libraries. You have Canvas, you have points, and in a way, I remember working with C++ computer graphics, and you could figure out many of the APIs by just looking what goes in and what comes out. And of course, that's why your approach works. But I was wondering whether you have any ideas or experience for what kind of APIs this approach works particularly well. Because I could imagine, on the other hand, for example, what G was presenting, if you test the REST API, of course, pretty much everything is generic. The same goes in, the same comes out, whatever you do. So for what kind of APIs does this work, or for which ones is it not well suited?
Definitely, yeah. So the API I showed in the example, from our experience with trying to test Skia, which is one of the main libraries we were testing, I think in general, the improvement you get using GraphFuzz versus a traditional fuzzer is really when there's a library that doesn't have that nice entry point for you to fuzz. So things like graphics libraries are things where you're where it's possible to invoke many different functions in different orders. Those are really the targets that we think get a lot of improvement from this. And actually, with you were mentioning just being able to sort of like infer the API by looking at what the function signature is. We do have actually some experimental work using Doxygen to parse the source code for a library and then try to automatically generate a schema. And we found that this works for like 90% of the functions that you pull out. And then sometimes you get weird cases where it's like a void pointer or like an array argument, and you sort of have to like go in and manually tell the computer what those are supposed to be.
Right, okay. And I mean, I'm going a bit out on a stretch because I'm not an expert in this area, but this this approach of plugging together let's say the different API calls and in a way getting a graph reminded me a lot on the early mutation testing approaches for like websites and so on, where you basically build a graph and then try to mess around with that. Do you have any ideas in that direction, or is that you feel that's a completely different area since you're mainly concerned with fuzzing, I suppose?
Yeah, so
it feels like if you already... Yeah, sorry.
Yeah, I'm coming more from a security background, so the mutation testing is a little bit outside the field. I think one area that's potentially interesting is when you sort of pair this API like plug and play aspect with coverage guided fuzzing. You can use feedback from the target to decide which API sequences are sort of interesting, and then you add those to a corpus and you can mutate them. And there's definitely a benefit you get from being able to get this coverage feedback.
Okay.
May I add to this point, because I was going to ask something about and you just mentioned it, the data flow graphs that you have. I was just wondering how you actually construct the graphs, and what kind of tools you're using to extract all this information, or is it all done with or self-implemented? So I was just wondering.
Sure. Yeah. So the schema is sort of the definition for the graph, and this is the part that the user creates when they're writing the fuzzer, and it's definitely the most time-intensive part for like testing a new target. In terms of graph generation, we basically split it into two pieces. So the first piece is we have a bunch of sort of predefined mutation rules. This is sort of typical in fuzzing. You'll define a list of like possible mutations. So these are things like we'll swap out an endpoint for one that has the same inputs and outputs, or we'll like randomly remove. And this leaves the graph in like an incomplete state, potentially missing edges. And so as a second step, we have this, we call it the edge completion algorithm. And what that basically does is whenever there's a missing edge, we replace it with a subgraph that generates that edge or consumes that edge. So for example, if we're trying to call a canvas method, but we don't have an input, this edge completion algorithm could fill it in with a canvas constructor. And in some cases, you actually need to fill it in with multiple endpoints. So if you think about like the factory model of like object-oriented programming, you need to like create an object, which then creates a different object, which then you can use. So occasionally the edge completion algorithm will actually fill it in with like a sequence of APIs.
Okay, thank you. That's very interesting.
Okay. Do we have any, first, before I go in and ask another question, do we have any other questions by people, so I don't block them?
So I want to have a question for Green. So do you consider about refine your graph during testing? Because initially you may have a very relatively simple examples to fuzzing. So after several rounds, you may have some domain knowledge about say libraries, and then you can generate more complex fuzzing template to further boost the fuzzing process.
Yeah, so this was definitely something that was we were thinking about during the research. So I noticed reading your paper, I really like the aspect of actually modeling, figuring out things that might not be correctly defined in the original schema definition. In our case, the fuzzer is really relies very much on the schema being correct. So we see, for example, in a graphics library, you might have a function that takes a float parameter that's supposed to be like an alpha channel. And so there's an assertion inside that function that says, is this between 0 and 1? And if not, it throws an error. And so especially when we're trying to automate pulling out these functions, we can fuzz these functions, but then we end up throwing floats in that immediately throw assertions. And so I think there's a lot of potential for doing some experiment during fuzzing. And if we consistently see that an endpoint is crashing, we can try to reason about what are the inputs that make it not crash and possibly just remove it from the schema or try to update the schema. But that's definitely future work.
Great. I have a question to Ralph regarding the specifications. And I mean, my background is also in the automotive domain, so I've seen a lot of what some of the companies are doing. And it's the cases I've seen, it's rather rare that you have sort of complete models of everything. So I was wondering, what's the level of completeness that you need to look at that your approach makes sense? You need to have like a model of a subsystem, let's say, that is reasonably complete, or where else of what is necessary?
Okay. For the approach itself, the consistency that we are trying to verify of course, just depends on the completeness. So if the models are incomplete, the verification would still succeed, but we might miss something then. But as you mentioned, typically the models are, or the systems are really, really complex. That's why we are focusing on smaller parts, subsystems. So for example, with Bosch, it's in the automotive industry, but it's specifically for controlling devices of the car. So it's not the overall system. It's always specific functions that we have. So for example, an automated cruise control or something like that. There, the models need to be to have it really. It's hard to say, but you cannot guarantee that the models will be complete. Our approach cannot ensure that. So that's a validation problem then in the end, and then that depends on the overall specification of the system and the requirements. So if we have all the requirements, then the system should be complete. But typically it's smaller parts that we are looking at, and these should be defined in a almost complete way so that we can make any statement about it.
Okay, but it's at least feasible that you say, okay, you mentioned cruise control, you have a safety critical function, and then for that one you do a reasonably complete model and consistency check. Yes,
because they typically have, if you go down the levels and you get really to the technical details of single components, then the models typically are pretty good, even if they're do not exist in a model-based form, but more within documents and specifications, and then these models need to be created according to these specifications and need to be complete and fit these specifications. Then we can make a reasonable statement about it. Yes.
Okay, thank you. Then let me have one last question for Yanji for the deep learning models. You had this comparison in your evaluation to Pythia that looked very impressive because you found 100% of these shape violations, and Pythia only, I think it was 23. And I was wondering, I don't know Pythia, so
Yes.
I'm not that familiar with that, but I was wondering to what level this is a fair comparison. Is Pythia also relying on some kind of specifications, or is it an automated tool that just automatically tries to find these issues?
Okay, I think this is the technique doing at which layer. Pythia 2 and also has two other related work is like a Pythia method, because they do the checking in the Python layer and use the parser to predefine the API extraction rule. So they lose, just like the first challenge, the hybrid programming model, they lose the
Right.
deep learning model computation graph structure. So they only extract each input-output tensor's violation error. So we observe that. So we need to dump the deep learning model's computer graph and do the checking on the whole graph, so to check more errors than the traditional method.
Right. Okay.
Okay.
So it's basically that they are on you could say on a different abstraction level where they cannot find certain things because the information is not there.
Yes. Is the Python old parser limitation. Okay.
Okay, then I do think we're pretty much done with the time. I would very much like to thank all the speakers. This was great fun and very interesting talks. And with that being said, a round of applause and enjoy the rest of the conference, everybody. Thank you very much.
Thank you.
Thank you.
Goodbye.
Bye-bye.
Goodbye.